Okay, well, uh, see, UCLA offers great professor-to-student ratio. Uh, anyway, uh, on Friday, I had started talking about sensing and kind of with the intent of talking about how to process sensor data, but on way to it, a little bit about sampling. And normally we think of sampling in terms of, I was talking about how sort of you do it with Nyquist rate, with the goal being one of reconstructing the signal, and we do it by sampling at twice the highest frequency. We had some discussion about that, how you have to make sure that there are no frequency components which exceed half the sampling frequency, because otherwise it's an irretrievable corruption of information. And also I had touched upon that it may be that you could get away with subsampling if your goals are different. Like, for example, if you don't seek to reconstruct the signal, or if you know more about the signal than simply that its frequency is something. Okay, so in the same way, normally we think of sampling purely in terms of time, but in many systems, particularly kind of when you have distributed sensors, what you're really doing is you're sampling in space. And in a sense, you have the same type of issues that occur over time now occur over space. It's just the frequency and all are in terms of the spatial dimension. There are a few things that do differ, though. In case of time, if you forgot to sample, then you cannot go back, right? Because this sort of the arrow of time, so to say, is against you. But in case of space, if you're, let's say, sampling a spatial field, and if you took too much of a step, then you could always go back and say, okay, let me resample that. More generally, though, you're sampling in space and time. Just something to keep in mind. But in case of space, a common technique often is that you do a sparse sampling, and then based upon where there is more interesting things, like more changes happening, you go and revisit and then sample at a finer level. Whereas with time, that kind of strategy doesn't work. But generally speaking, sampling costs something, costs energy. In some cases, sampling also costs privacy, as in, let's imagine you are in a setting like a military operation or something like that, and the act of collecting the sensor data itself can be a giveaway, like you have to fire up your sensor and all, and that can be detected. So oftentimes you want to minimize how often you are sampling for a variety of these reasons, and that's the topic that we'll cover next. Another thing I wanted to go over a little bit is, let's see, so if we look at the overall cycle, if you are doing a sampling in time, so the very first stage that, so you start out with some sort of an analog signal, and the very first thing you do is this anti-alias filter, so a low-pass filter which removes all the frequencies that are not acceptable. And this is when you are sampling using kind of the Nyquist criterion. Next thing is that you do this sample and hold operation, which basically results in sort of at certain points in time you are getting the you're getting the analog value. So basically some sort of a capacitor in which you store the charge corresponding to the amplitude of the signal. And then you do quantization of the samples. So you take these samples and then one of some levels that you are willing to quantize to it. So, and then finally you get the digital bit. So there are two things happening out here. There is discretization in time, and there is a discretization in value. And both of them basically add noise, so to say, if not done properly. So there is quantization related noise, and oftentimes the challenge that you may face is that there may be more useful information in some region of this space. So then instead of having these levels be uniform, you may have these levels be non-uniform, like more bits focused on the part of the signal where there is more important stuff happening, and then fewer bits far away. So non-uniform quantization could be done. And likewise, in the time dimension, if you are able to meet the Nyquist criterion, then you have perfect um, uh, reconstruction of the signal. But our goal tends to be, could we minimize that effort? And then again, you can imagine same thing, that signals often have interesting thing happening in some part and not so much there. Perhaps you can focus your sampling when interesting things happen. So like, for example, if you think of like a ECG signal, for example, it's kind of mostly flat, and then suddenly there's a burst of stuff, and then again flat. So maybe you can focus your samples when the interesting things are happening. So you could, at least at an intuitive level, imagine sort of moving away from kind of this common paradigm of uniform quantization and uniform sampling in time.
Can you give an example of sampling in space?
Sampling in space, yeah. Let's say, for example, you are trying to monitor weather-related things, right? I mean, or pollution in a city. You are trying to find out how traffic affects pollution. So you are sampling the pollution field, like what's the concentration of particulate matter in the air in a city. Okay. Now, one way you could do it is you can just imagine that I can create a grid of sensors in the city and just measure that. But maybe alternative could be that based upon some initial study, I can say, you know, most of the interesting stuff is near the freeways, so I'm going to focus my sensors there and then have sparser sensors elsewhere. I could even make use of mobile things like a moving sensor, which kind of does a pass and then identifies areas. But that's an example of a spatial field. Pollution, sound, light levels, right? Or at a planetary scale, when you kind of try to do weather phenomenon and all. So those are all examples of spatial fields. Okay, and then also, yeah, in applications like photography and all, you again have spatial fields happening. I mean, you can think of a camera image as nothing but spatial field which you are sampling. So it's a bunch of sensors in space, and then the number of pixels in your sensor are basically going to dictate what all you can capture or not. Okay. So and more broadly, space and time both, right? But kind of concepts apply, the similar concepts that work in both cases, other than, like I said, time always keeps moving, whereas space kind of, you could quote freeze in a way, right? You can go back and revisit it. Okay, so another thing that we often encounter is this notion of upsampling, downsampling, and decimation. So oftentimes when we sample at certain rate, that may not be what we upstream, or rather downstream when you're processing it, may be needed. So oftentimes you need to change the sample rate. You may have sensors which are providing data at one rate, but maybe your processing algorithms assume that the data was at a different rate. So now you may have to digitally change these things. So upsampling refers to changing the sample rate upwards, and downsampling changing the sample rate kind of downwards, and decimation and downsampling are kind of closely related, so I'll just talk about it. So in case of upsampling, I need to, let's say, increase the sample rate by certain integer factor. Then basically you can think of it as inserting zeros between where previously sample used to be. So that would be one approach, right? So I have some samples and I'm multiplying it by, so I can insert something. So one strategy could be I insert zeros. The problem with that is that it can yield distortion now. So you generally tend to have better ways of doing it. So better ways of interpolating at those points. So sinc interpolation. So sinc function is what we use for reconstructing from samples back to the original waveform. So in this particular case, a sinc interpolation can be done.
Yeah. Can you just not do a linear interpolation?
You could. They're all going to have. I mean, these are all at some level going to be heuristics at that rate. But you could conceptually think of it this way: that I can I can take my samples, I can reconstruct the signal, and then I can resample it, right? And since I'm sampling it at a faster rate, I'm okay, right? And that would be the best thing to do.
Yes, but adding zero sounds like counterintuitive because
No, so adding zero is a lousy scheme. Adding linear is less lousy, perhaps, but they are all going to introduce distortion. The best thing you can do is a sinc interpolation, because when you reconstruct, you do it using the sinc functions. But so conceptually, if I can always because if my original signal was sampled with Nyquist rate or higher, so therefore given a sample stream, I can reconstruct the original signal and now resample it at a higher rate, and that's perfectly fine, because the signal was already band limited to whatever. Let's say my initial sample rate was x, so that means the highest bandwidth was component was x over 2, highest frequency component. So now I can reconstruct it and then resample it at a higher rate, and I'm good to go. Okay, so upsampling conceptually is easy, and really it's about managing the computation complexity. Downsampling is trickier now, right? Because downsampling, yeah, go ahead.
So between, like, we covered in two strategies. One is interpolating the samples, and the other one is like
full reconstruction followed by resampling.
Right. So which one is better?
Well, the latter one is certainly more accurate, right? Because I perfectly reconstructed and then I'm getting a perfect resample, but at more computation cost. Okay. Decimation is the downsampling is tricky, because now if I want to downsample, then I can't simply let's say I give you something sampled at 100 samples per second, and I say, hey, I need it at 50. So your intuition will say, okay, let me drop half the samples, or maybe average 2 of them and then use that, right? I mean, so take windows of 2 samples, average them, and let's say use those. Problem with all of those is that you may be violating the original criterion that we have for perfect reconstruction, which is that the frequency component should be less than half the sampling rate, and if my new sampling rate is 50, I need to make sure that the frequency component is less than 25. So again, the ideal way of doing in this case would be that you reconstruct, then you filter, and then you resample. Okay. Again, all of these things come at cost, and oftentimes, of course, you see these things where we just average and all, and so that's with the implied assumption that we were way oversampled to begin with. Okay, that's kind of the implicit assumption that sort of goes in there. So basically, just blindly throwing away samples or doing some averaging kind of will incur artifacts. Okay, and then you can always imagine handling rational things like L over M kind of thing in this example. So I want to change the frequency by 2 over 3. So that's a combination of upsampling and downsampling. So these kind of games often have to be done. The other thing to remember is each sample that you collect not only incurs energy in the act of sampling, and sometimes the sampling is not passive. Sometimes sampling requires emitting energy, like let's say for a radar to take a sample of the space, it has to send out a radio signal, or if it's dark and a camera to take an image, it has to shine the flash. So the act of sampling can be pretty energy hungry, or for example, the PPG sensors in your watch, in these smartwatches or Fitbits, they have to shine an LED and then measure things, right? So they have to actively transmit energy. So act of collecting the sample can be pretty energy intensive in some cases. And the other thing is every sample you collect has to be processed. So therefore, it's important that we be parsimonious about sampling, because that has burden all through there. And intuitively, if you think about it, Nyquist sampling is obviously not very good, because we sample and then we compress, and if we were good, then we shouldn't have to compress, right? Because that means that our sample clearly had some redundancy of information. Likewise, resolution. Sometimes you maybe have excess resolution, which is unnecessary, and again, more the bits you have, more the processing overload that you are putting. Um, and so what all of that leads to the following: that could we do better on our sampling strategy? And like I alluded to earlier, kind of two things help you. Number one, I may not be interested in reconstruction. I mean, like usually we are not interested in reconstruction. Usually we want some function over that waveform, right? I mean, if I'm getting a radar waveform back, I don't care about the waveform. I want to know, is there a human being present there, or what is that person doing, or things like that. There's some function we wish to compute. And the other thing is that maybe I know more about the signal than simply its highest frequency component. So, and finally, at an intuitive level, what helps you is the knowledge that usually when we capture these signals, we are able to successfully compress them, which means that they obviously had informational redundancy. So some years ago, like a dozen years ago or so, kind of this whole thing became very sort of hot, if you may, in terms of research concentration, that could we do better? Could we have just the optimum amount of sampling being done? Now, in purely mathematical terms and all, I mean, there had been work in decades before also, but I think just the technologies and everything and the interest sort of happened in the early 2000s. So this led to this whole area called compressed sampling, or compressed sensing, or compressive sampling. There are kind of variety of names, and there are other related areas like sketches and all. But the basic idea being that instead of this dense sampling, which could we get away with something which is more smart. So the intuition behind these things kind of is the following: that let's imagine that if we are looking at sort of a signal in a frequency in the frequency domain, then what Nyquist sampling basically says is that twice the frequency, or actually more precisely twice the bandwidth, as in the highest frequency component minus the lowest frequency component, twice of that is sufficient to, if you were to sample a temporal signal with that, then you would be able to reconstruct that temporal signal. But if you look at the spectrum, I mean, there is not much going on. There are kind of 4 peaks out here, and there is really none, the signal is basically dead elsewhere, right? In this case, it's kind of summation of 4 sine waveforms, for example. So what's happening really is that there is interesting stuff which happens in some places and not elsewhere. And you can imagine the time domain counterpart when I was talking about the ECG signal. There's interesting stuff when those peaks are present, but not elsewhere. Of course, the challenge is we don't know where that uninteresting stuff is or not beforehand necessarily. So what compressive sampling allows you to do is to really sample at a rate which depends upon the actual information content in the signal, as opposed to making a worst case assumption. So you can think of that Nyquist sampling was making the worst case assumption that between the low and the high point in the frequency, the spectrum could be arbitrary. That is, all the coefficients may exist and they could have totally arbitrary values, but your particular signal may not have that characteristic. So could we be smart about sampling and collect fewer samples? Now, of course, collecting fewer samples will have to come at a cost, and usually it's at the cost that our decoding becomes harder. So originally we just had these uniformly sample things, and we basically do sinc interpolation, which basically says that I take those values multiplied by the sinc function and then add them up, and I get my signal back. But now things get, generally speaking, trickier. So my compression side, the sender side or the sensor side, becomes more efficient because it's sampling less, okay? But the decoder side becomes more complicated. But that's fine usually, because usually sensors are on the more resource constrained devices, and decoding may be taking place in a cloud service, for example, right? So, and meanwhile, by doing, if we are able to do compressive sampling, then we can get away with it. So normally the way things happen is that we sample, we compress, and then we do things here. So right, so we sample fully at Nyquist rate, we compress, communicate and all, but now could we instead, with compressive sampling, we do in effect compression and sampling simultaneously, okay? And then decoding becomes harder on the other side of the comm link, but that's a fair trade-off to have because we are eliminating kind of the compression related things and get away with a simpler processor, and A2D has to do less work. If you never capture the sample to begin with, then you are better off. So what happens in compression? So very broadly, compression is basically about removing redundancy, so that I take my input and produce something which could be decoded back to the input, except that it requires fewer bits to go across. And there are lossless versions of it, and there are lossy versions of it. And we encounter these things in image and audio and such signals kind of all the time. So for example, JPEG is a lossy image compression. Anyone knows file formats which are lossless image? PNG. Yeah, PNG and GIF, right? These are all lossless. Well, GIF is just an image, PNG is a lossless compression. Okay. Okay, so lots of algorithms kind of exist, and of course, if you are lossy, then you are kind of trying to make use of the fact that that amount of loss is acceptable for reasons of perception or whatnot, right? So those kind of things come into play. What happened?
Shouldn't zip be less than? Is like zip of better compression than PNG?
PNG is better here, right? Fewer bytes.
It depends on the signal you're trying to.
Yeah, of course it depends. But I mean, PNG does take into account the similarity of neighboring pixels. Okay, so it does. It's a domain-specific compression.
Yeah.
Generally speaking, you would expect domain-specific compression, domain-specific lossless compression doing better than a domain-agnostic one.
That's
Right?
right.
There are, for examples now for genomic data, stuff like that. There are specific forms of compression things that sort of exist. Okay. Don't read too much into these numbers, kind of, but the main point basically is that yeah, these things exist, and zip is not really the best lossless compression that is around. There are better things now, and likewise on lossy image side, there is lots of development that keeps happening, and all the major companies, for a variety of reasons, kind of keep pushing out new things. Okay, so so what happens in some of these things, like for example JPEG, what you do is you convert the image, at least a classical JPEG, you convert the image into a different domain, discrete cosine transform, and then you kind of compress in that other domain. Okay, so oftentimes the compression is easier done after transforming the input into some other form. So now let's imagine that I have a sine wave, okay, and I seek to compress it, right? So, I seek to sample it, right? So one way of thinking about, and with the goal of reconstruction. So if I were to just look at this with the FFT, then whatever is the frequency, in this case 12 hertz, so I would say, okay, I need to sample at 24 hertz. But you are looking at this, you can also see that that seems highly redundant, because I can describe the whole waveform using just 3 parameters, right? I mean, there's a frequency, there is a amplitude, and then there is a phase, right? And those are the only 3 things, and then I am good to go. So if I were to tell you that my source is like that, then I need to just capture sufficient samples to be able to estimate these parameters. And if you're lucky and your measurement is not noisy and stuff like that, 3 samples are enough for this purpose. Another way of looking at this thing is that if I look in the frequency domain, then basically my spectrum has a single peak. And so now I need to know kind of which coefficient it is. So like if I have an endpoint f50, then which one is non-zero? So I need a ID for the coefficient number, and then I need, say, complex amplitude. So again, 3 parameters. So whichever way you look, 3 parameters is all I need. So by looking at the problem of sampling and kind of from the perspective of what is the real information content, then you could potentially do things. You can potentially do things better. So, and I'm sure some of you have done signal processing courses. You might have seen other things like PCA analysis, stuff like that, which again kind of try to find the dominant informational component of a signal and kind of focus, basically like grab those first. Okay, so there are many different approaches that one can do. So if I am able to transform my signal into, quote, the right domain, then the sparsity in that signal may stand out, and then I can basically focus on sampling or grabbing those coefficients that are important. So this is an example. There is some speed signal. You look at this time waveform, it kind of looks kind of complex. You look at the spectrum, you see that a lot of the energy is focused on certain coefficients, and therefore what I can do is I can basically just focus on some top coefficients. Okay, it's kind of, again, when you look at PCA kind of thing, some top eigenvalues. Okay, in this case, some top coefficients, and the rest are assumed to be 0 because they have very little energy. So my revised spectrum look like this. I go back to the time domain, I have this new signal, which kind of looks like that. Okay, so that's the concept. So if I could somehow view this thing as a sampling problem in a different domain and then focus on the more interesting coefficients, then I'm kind of good to do. So this is in effect what happens when we do compression in like JPEG, where you go to the discrete cosine transform domain and you play the same game. Okay, so let's go back to our sine wave example again. So we want to sample this sine wave is x of t, and we don't want to do the Nyquist approach. So instead, we know that it's a sine wave. So the question is, how should I now go around doing it? Well, in effect, you can view the sampling problem now as how many samples do I need to collect so that given the values of those samples, I can reconstruct the signal, which is equivalent to saying that I can estimate the phase, amplitude, and frequency, right? So essentially, I want to collect as many samples as are necessary to then go collect all the parameters of my model, my source model. So variety of ways to kind of potentially approach this thing. So for example, I take the original signal, I can sample it above the Nyquist rate. So for the moment, imagine that I don't really care about the actual sampling. I'm going to sample at the full rate, but I want to discard and then only ship to the cloud just a smaller number of samples. So I'm really worried more about the cost of sending it over the cloud, over the network to a cloud server. So I sample above the Nyquist rate. I'm going to get a bunch of F50 samples, and then I basically sort of extract just those samples which have the high energy. In this particular case, there would be one particular coefficient, and I send those things out. And in this case, as long as your FFT has sufficient number of points, I would be good to go. So remember, FFT itself is doing a frequency discretization. So it's possible that the f at which the sine wave is occurring is not precisely at one of the FFT coefficients. Okay, so the finer the granularity, the better off would your estimate of f would be. Okay, so so one could imagine kind of doing things like that. One could also do things in kind of analog domain, okay, where basically what I can do is I can make use of a PLL to then tune it and to find until the frequency matches, and then I know I now know the frequency, and I can send that frequency out. So in effect, I can work it that way. But the third method is what we are interested in, which is this. I want to collect samples to begin with this model in mind. So intuitively, since I have three parameters, then three samples should suffice. So let's consider a simpler case. Let's say we knew the frequency of the sine wave, and we only need to measure its phase and amplitude. Okay, so I can, in principle, take two measurements and get away with it. The only problem is, if I'm unlucky, then these two measurements may not be terribly informative. Because if the two measurements happen to fall at the same point in the waveform, then they are not going to add any informational value to me. So these two things have to be appropriately located. But if they are, then in effect I get two equations, right? I have a measurement Z1 at time t1 and measurement Z2 at time t2. And since we already knew the frequency and we know it's a sine waveform, so I can write down the equation. And it has two unknowns, A and phi, and I need to solve this thing for A and phi. Now, you could imagine extending this thing to kind of a richer source model, maybe a model which has summation of two sine waves, so you'll have more parameters, but you can imagine kind of keep writing these kind of equations and then doing a parameter estimation over that. So another method which we could do is I can do a search. I know the frequency, so I can take waveform of that frequency, and then I can do a correlation until I hit a peak. And that way I can get the phase, and I can do the amplitude estimation using this template matching kind of approach. So that's another approach we could do. Or a final approach you can imagine doing is that we can basically treat it as a optimization problem. Okay, so I have these equations. I want to solve for A and phi such that some error criterion is minimized. Okay, and now my reconstruction problem is nothing but some sort of an optimization problem. Now, in this case, so at least conceptually, in this example of knowing the sine wave, I could exploit it in multiple different ways and also reconstruct the signal. More generally, though, could we have a scheme which works for more general signals? Now, fortunate part is that natural signals often are compressible. We know they are compressible because we compress them, right? I mean, we take these, and the reason is that most natural phenomena are generated by some low dimensionality process. Okay, these are not, it's not white noise coming our way. It is these are being generated by some inherently lower dimensionality process, and whose noisy signal is what we are kind of observing. So compressed sensing seeks to exploit that. The question then becomes, how do we know what space to sample them in? Okay, so could I take my signal and project them into some space like the frequency domain where it is going to be sparse, so that I can do things there. So what compressed sensing kind of showed was the following, that uh, um, we can view this process of sampling as kind of a process of matrix multiplication. So let me get back to it, but get to that. But on this slide, the point I'm basically trying to make is that because my even though there were only 2 parameters, if I were to sample it just very minimally, I may not get a great signal out. So sometimes you may have to oversample. That is not precisely the number of parameters, but some additional points. So each one of these red dots is indicating that. So in this particular case, what's happening is that there are 3 samples, 1, 2, 3, and the reconstructed signal came out to be this, because these points had, these measurements have their own error, and they're just too few. So even though the parameters were only 3, if I just minimally sample, I don't get a very good reconstruction. But if I do some additional samples, but still a lot fewer than what Nyquist would have suggested, right? In case of Nyquist sampling, I would have a sample happening every cycle out here, actually 2 samples happening every cycle. So in this case, these are 11 samples, and then I basically get a very good reconstruction. The bottom plot is the reconstruction error. So compressive sampling works in this case. That whole strategy of taking fewer samples, thinking of it as a optimization problem of parameter estimation works great with lot fewer samples than you would imagine otherwise. Okay. Now, can I generalize this thing? So what happens now is that I, in general, would have some signal x, and I basically want to find out that I want to sample it at certain points. So that's the red dots which we are doing. And in essence, that boils down to that I can think of my signal x, which is like a long vector, if you may. Let's say it's a vector of what Nyquist rate sampling would have done, and now I'm going to sample it at only certain points. So you can think of it as multiplying it by random matrix, and z corresponds to that. So this is a sparse matrix where the ones indicate what I'm sampling. So essentially, if I had phi as an identity matrix, then that would have corresponded to sampling as it is. But if I replace that identity matrix by a random matrix, then in a sense what I'm doing is I'm taking random summations of some of the samples. Okay, summation of some of the random samples in my original vector. Okay, so phi is a random matrix like that. And it turns out that a lot of natural signals, if sampled this particular way, okay, and with z being a lot smaller in dimensionality than x, so you see that phi is as fat as x, but its height is very little, so that means I have very few samples. So I started out with a long vector x. By multiplying it this, I end up with, and it turns out that if you do this kind of random projection, then for a lot of signals you can kind of go back and recover things, because there exists this natural sparsity in real world signals, which this approach kind of ends up exploiting. So my sine wave example could be thought in this manner, right? That originally I had a long vector of potential samples, and then this sampling matrix phi is basically collecting some samples. In this example, it's just selecting 3 random samples. In general, the model could be, I may have in the same row multiple sampling points, in which case I'm going to add them up. So I'm taking a projection there, but kind of the concept remains very similar. So the advantage of this way of thinking is that I don't need to know a priori which dimension, which space is the signal is the signal sparse in. If I knew, so for example, for some signals we know that they are sparse in frequency domain, or they are sparse in time domain, or some other domain of interest, then I could certainly exploit that. I can project the signal there and then sample there. But this strategy that I had on the previous slide This strategy is just for any general sort of time domain signal, basically. Okay, the problem. So the compression part is basically this random projection. Okay, a common way in the time dimension, and you can imagine your A to D converter now being driven by this phi matrix, basically. Okay, so or at the software level, it's basically saying instead of telling my A to D converter to sample periodically, I can basically do triggered sampling, as in I can. So usually these A to D converters let you basically tell them go ahead sample at 1 kilo sample, but now you can have some software generating point toss or something based upon this random matrix and then driving the sampling process. Okay.
If I implement something like this on edge device, so like these matrix multiplication would be computationally more intensive than.
No, remember I'm writing it as a matrix multiplication. All this is saying is where you are sampling.
So you can have a lookup table.
Yeah.
Like,
So instead of sampling at every sampling point, I'm sampling at certain points. Okay, that's all that is happening. Okay.
So it's actually less computationally intensive than.
Yeah, if done right.
Yeah.
Okay. I mean, the flip side is now if you're simply doing it on a standard microcontroller, then the software is doing some more heavy lifting, whereas previously it could simply tell the A to D hardware go ahead periodically sample. Okay. Whereas now it has to be done. But everything else is reduced. You have a lot fewer samples. Okay, to the extent that if you Google for this term single pixel camera, okay, this is some pretty cool work out of Rice University. So there are certain cameras where pixels are super expensive to have. I mean, we are used to whatever gazillion pixels in our cameras now, but there are like infrared cameras and cameras in other parts of the spectrum where the pixels are very expensive to have. So reducing the number of pixels is important. So this Rice camera, what it did was it had a single pixel. By that I mean there's a single sensor as opposed to an array of sensors. Okay, and then using mirrors, they would arrange light rays from different directions to fall on this thing. So sometimes this pixel will measure a light ray coming in this direction, another time in a different direction. So essentially, it was sampling the light field in different directions as opposed to sampling it densely. And then again, they showed that they are able to reconstruct images. So this stuff is for real. I mean, you can drive things down quite dramatically.
So instead of taking one samples with multiple sensors, they were taking multiple samples.
Samples with a single sensor, but a lot fewer samples than otherwise.
they only have to sample like the angles in
Like in my example, if that with that sine wave, so if I were throwing at you, if all I told you is that the signal is a sine wave, I don't tell you any. Okay, as opposed to originally in the Nyquist regime, I was telling you the signal has a maximum bandwidth of 20 hertz, right? This time around, I'm telling you signal is a sine wave. Then, as the previous thing showed, I can reconstruct it with very few samples, and now you can say, okay, you know, at any given time the signal is a sine wave, but it changes periodically, right? So we are going to re-estimate it. Now imagine if it's not just a sine wave, if it's a summation of a few sine waves. So instead of a single FFT coefficient, there are, let's say, up to out of n, maybe up to some k FFT coefficients which have values, right? So you can think of it as a summation of k sine waves. In that case, I will have 3k parameters. Okay, again, a lot fewer than order of n parameter, right? In the worst case, I have to sample all the n FFT coefficients, so 3n parameters. So if I am basically interested in the top k, right there I have a compression gain. But there I am making use of the fact that it's a sine wave. With this approach, I don't even need to do that. All I'm doing is I'm doing sparse sampling, and I'm going to try things out with different matrices. Then the reconstruction problem in this process. So now our sampling looks like this: z equal to phi x, right? Then what the objective of my reconstruction is that I want to find a vector y that meets the constraint and is the most compact representation. So let's think of it this way, that y is equal to some other matrix psi x, then I can kind of rewrite this thing is equal to psi phi inverse y. So my goal then becomes that the reconstruction problem becomes that I want to find a y such that, and this is z equal to this, okay, so such that this constraint was met, and there was some sparsity requirement. I want small values of the parameters. Details don't matter so much out here, but main thing is that there is a hard optimization problem that you got to solve. In effect, what you're doing is that after that sparse sampling, you're trying to find a best match signal, which is in a sense what we were doing previously. We were trying to find that combination of those three sine wave parameters such that if I were to sample that signal, then it would have matched very well with what I was originally getting. So I translate that interpolation way of reconstructing the signal to one where I'm trying to find the best matching signal, the signal which best explains the parameters I saw. Okay, so I try out lots of sine waves until they matched the parameter that I saw. So it's the equivalent which is kind of happening out here. So this is a kind of a so ideally you would like to do it under L0 norm, which is basically saying that how many coefficients are non-zero, which is essentially the sparsity requirement. Okay, but it turns out that if you continue to do very well, even if you do with L1 norm, and the results are pretty good. So the main point is under some appropriate conditions, you are able to get sort of great results with this kind of approach, and these things work pretty well with a lot of natural signals. Like there are people applying it to ECG signals and EEG signals and accelerometry data and stuff like that. I mean, all sort of stuff. But at the cost of decoding now becomes a lot more complicated. Okay, as opposed to interpolation. So there's some pretty. If you just Google for it, you'll find lots of things. I'm sure there's some course or the other that covers it. I don't know, any course at UCLA covers compressive sampling?
So,
Anyone?
compressive sampling, well, like there's like classes for computational imaging that
applied that. Yeah, I don't think there's any dedicated course here. Although interestingly, Professor Terence Tao, our field medal winner, he was one of the, along with this guy Candes, who used to be at Caltech and is now at Stanford. They had some of the early papers in this space. So UCLA played an important role in this space. This is around 2005-06 kind of time frame. So so that's compressive sampling. Okay, so you basically so again, if you know a lot of, so general concept, if you know about the signal, then you can basically focus on and when I say know about the signal, basically what I'm saying is that you know a low dimensional parametric representation of the signal, like in case of sine wave, or that you know some space, some projection of that signal where their signal is very sparse, so that if you sample in that space, then you can get away with a lot fewer samples. Okay, and sometimes if you're lucky, your signal is sparse in the time domain. ECG signal is a great example of that, right? I mean, it's kind of stupid to sample in its flat region, so I can focus. So clearly, there's a lot of sparsity there. But oftentimes you don't know this, right? Which domain, how to transform to get that sparsity. And so what this compressive sensing thing showed was that these random projections work pretty well. Okay, and then formulating the problem in terms of this L0 optimization or its approximation as an L1 optimization works pretty well. Okay, so yeah, around a decade ago or so, this was kind of, there were large funding sort of large funded programs and all focusing on like better A to D converters. Essentially, instead of sampling data, you're sampling information. That's really kind of the distinction out here that's happening. So, so yeah, lots of interesting work, and there were around that time, there were analogs in theoretical computer science and all, which were again similar things. Like there's a concept of sketches, which was very similar. In general, you often face this issue that you want a compact representation of something very complicated. It could be a large social network, it could be a long, dense time series. There is a certain commonality to it, and the idea generally is that if you can exploit structure that is underneath that signal or underneath that object, then you could be smarter about sampling it, okay, and have a better representation. Okay, so that was compressive sampling. Another idea which has also existed is kind of driven by more intuitive notion, which is if I look at a signal, temporal signal, spatial signal, then it's so obvious there is interesting things happening at some point and not others. So could I exploit that? So look at the sine wave, right? I mean, you could say, you know, there's a part of the sine wave which changes slowly, and there's a part which changes more rapidly. So intuitively, it would stand to reason I should sample more when things are changing more rapidly and sample less when things are flat. So if I'm sampling, let's say, light field on the floor of this room, this area is totally flat, but there are some highlights and there are some shadows. So wherever there are transitions happening, maybe I should sample more, and wherever things are not changing, I should sample less. And another intuition could be when interesting events happen, right? I mean, so I could focus my attention there. So this has been another kind of, if you may, part of research community which has examined these kind of approaches also. Now, in a way, compressive sampling provided a universal solution, right? I mean, for these. And if, of course, if you have a signal which is dense in every possible way, then compressive sampling is not going to yield anything, but otherwise it does. But are there other ways we could accomplish this also? One other thing I would say is also that while in theory some of these things look very appealing, but if you peel one level, things are not always as they are. Okay, so one of the nice things about periodic sampling is that I can just send you a sequence. I just tell you up front, this is a signal sampled at whatever, every millisecond, and then I just send you a list or whatever, an array of numbers, and you can assign the sampling time to it based upon just the starting point. So if I tell you it's sampled at every millisecond and the starting point is 5 p.m. and then all I need to give you is the set of values, sequence of values. On the other hand, if I am doing compressive sampling, then for each sample, I also have to tell you the timestamp. So don't ignore that, because that also needs to be conveyed. Therefore, so some of the benefits of these smarter approaches, which are sampling irregularly, goes away once you also take into account that you also have to carry this additional timestamp data, which you are going to need on the other side. So just something to bear in mind. Okay, so back to this thing. So consider kind of a very simple control system that basically is measuring through some sort of a sensor, position encoder, the position of the motor, and then there's a command which wants the motor to be in a certain position, and the controller kind of keeps that. Okay, so we encounter these kind of systems in many places. And then what happens is in a digital system, we would have an A to D converter, and therefore kind of this whole digitization is happening. So what typically the way these systems are done is much like what was happening on the sensing side, which is we periodically sample at this ADC converter and feed it out here, and there is a periodic update of the command that goes on. And the period at which we sample is dictated by kind of the overall dynamics of this system. Okay, that is kind of the loop bandwidth, if you may. So there's a bit of a black magic which happens to decide what the appropriate sampling rate is, but generally speaking, you would imagine that if my system, here is a motor, but it could be a fighter pilot, an autonomous car, whatnot, If it is more agile, then I would need more rapid sampling. On the other hand, if it's something more sluggish, then it would be a slower sampling thing. But there would be some sampling period like this. And then motor controller will compute digital value of the command to apply, and then we'll go through a D2A converter to actually apply the voltage out here. And the algorithms out here can range from super simple stuff like I'll measure the error between the current position and the commanded position and multiply it by some constant to, so that's called proportional control, to proportional derivative, proportional integral, all these kind of things, to fancy model-based control where I may have a model of the mechanics of this system and then take that into account out there. So all sort of stuff. Point though is that every sample that I digitize out here needs to be processed. So the computation load here is directly in proportion to the number of samples I capture. And the question then becomes, much like which we faced earlier, that where every sample that we captured from sensor needed to be processed and sent, same thing out here. Every sample that we capture needs to be processed. And many modern systems, the sensor sits somewhere different than where my computer might be sitting. So the data which is driving my control system in general may be across a network, and therefore there might be issues of bandwidth as well out here, processing, energy, all those kind of things. So what this leads to is the following, that normally we are sampling the signal in the periodic manner, as I said before, and this is called as Riemann sampling. Okay, so this periodic sampling. And control systems, much like sensing systems, behave the same way. But on the other hand, that intuition that I was suggesting earlier, which is when signals are changing more rapidly, perhaps I want to sample more frequently, and when the signals are more stable, then I can afford to sample less. So if I know that the motor is in the stable mode, I can pay less attention to it, right? Sample less, update less frequently. So this is called Lebesgue sampling, okay? So it's playing on that same intuition that occurred in the question though is, how do we decide when to sample? So previously I just gave the intuition that if things are changing more rapidly, I sample again, right? So you could imagine that I can keep measuring kind of the d over dt or d over dx if it's a spatial signal, and based upon that kind of go. So if I see that the light field was changing a lot, my robot will make a smaller step, and if it's changing a lot, I'll take a longer step. Or likewise in the time dimension, you could imagine doing. So now, fortunately, in sensing, this is always a tricky question to answer. So for example, I'm monitoring an incoming time signal, and I have to decide how much to when should my next sampling instance be based upon what I have learned thus far. And if I am wrong, I could be wrong in one of two ways. My step could be too large, in which case I have missed information, and therefore my inference would be incorrect. And if my step is too small, then I have basically made an unnecessary sampling, so I'm being less efficient. But the problem in open loop sensing is that you never know, because something you never measured, you have no way of knowing whether you missed it, right? I mean, so for example, if I take my blood pressure every morning, and if my blood pressure goes high during evening times, I will never know that, right? I mean, because the model was intrinsically violated. Control systems do, although have an advantage in this regard. If I don't sample enough, then the system will go unstable. So in control field, and this is actually Professor Paulo Taboada's work that I'm describing, it's a very well-cited paper of his, basically have a well-defined criterion, which is how much should I sample so that the system remains stable, right? Relative to my uniformly sampled system, I could try to come up with a strategy for this non-uniform sampling or Lebesgue sampling, so that my overall system still remains stable, okay, and I can design things for that. So that's what this work does. So in effect, what happens in the system, sorry for my awful choice of colors, hopefully you can read it. What's happening out here is that the ADC, instead of being driven by a periodic clock, as would happen in the Riemann sampling, now has some sort of a computation which is observing what we did previously, which is observing the analog signal and then driving the ADC. So it's basically triggering the ADC when it is worth collecting an additional sample. Does someone see some issue with this picture?
How is it observing the signal?
How is observing the signal? Exactly, right? I mean, I just said that I want to collect the signal, but now I'm giving you this unit which is observing the signal. So, well, I guess partly answer would be it does it in analog domain. Okay, that could be one cop-out answer. Another cop-out answer is no, it does it digitally, but it doesn't do it exactly. It doesn't approximate, it does a prediction, okay,
Yeah.
based upon some model, okay? So one of two approaches. You either do it in analog or you do an approximation. So you don't actually monitor it, because if you were to monitor by digitizing, then that defeats the whole purpose anyway, right? So you'll have to do it one of two ways. Okay, but you do know when you last sample, you know obviously the history of what you have sampled, so you can track the changes of the signals. But then we are kind of back to the sensing problem in a way, right? I mean, we are basically saying, based upon something about how rapidly the signal was changing, I could do it. But you could do better because you do know something about the plant, some model of the plant, perhaps you've learned it, and therefore you could incorporate that, and you can be cautious that, you know, I know that if I take too long a step, then the system will go unstable. So I kind of basically predict what the next sampling instant should be in a more judicious manner, okay? And in a control system, typically the way these systems are designed, kind of you do know about the plant that you are trying to control. If you know nothing about the plant you are trying to control, then essentially you are in the open loop world. If your plant can behave randomly from instant to instant, then there isn't much that you can do. So, but this little intelligence can help guide the process. So, in sort of, I think this is like 6-7 year old work. They came up with some criterion which basically that if the current value of the analog signal has changed significantly from the value as it was at the last time I sampled it, then I should sample it. And the criterion was some particular sort of scale version of the norm of the current signal. So this is how the condition looked like in their sort of work. And as you can see that I could compute it in the analog domain, right? But it will require me to implement a comparator, and it will require me to implement an absolute function and a subtraction. So you could do it. It's not that outlandish entirely in analog, okay? But alternatively, you could just do a approximation of it. In effect, you are trying to predict at what t would this, based upon what I have seen thus far, at what value of t would this condition get violated, and then do it entirely on the digital side. So what this, so this version where you do in the analog is called event-triggered control. In essence, I'm seeking an event where this condition is matched, and then I trigger the A to D converter. And then there is self-triggered control, which is basically instead of doing things in analog, which in effect is saying monitor x of t all the time, I basically do it through some knowledge of measurements that we have made thus far, plus a model of the system. I try to predict what the next sample time would be, and then repeat this process. So in that case, it's called self-triggered control, in which case you don't need any monitoring of the continuous time signal. But of course, this makes an assumption, which is I know the system dynamics well enough so that my prediction would be good enough, okay? And that remains. So self-triggered control, in essence, basically what it is doing is trying to predict the next sampling instant based upon some requirement. Now, the other way that you could apply, the needless animations out here. Okay, so the other way you can apply this thing is that I don't worry about the A to D converter at all. My A to D converter operates in the Nyquist regime, okay? And I'm only worried about which samples to send out. So I sample everything Nyquist, I have a dense time series, and now I'm picking samples out of it. In which case you can apply these schemes very easily because you have all the digitized sample and you're just basically looking at, it becomes kind of like a compression strategy at that point. A compression strategy where you are basically selecting the samples to send as opposed to doing anything funkier with them that more other compression schemes might. A nice thing about just sending the samples as opposed to coming up with some totally different transformed representation is that you can still do a lot of computation over them. Like for example, I may still be able to compute statistics like average and stuff like that there easily because they still, I'm still sending samples, it's just that I'm sending fewer samples as opposed to like if I were to ask you to do some operation on find edges in a JPEG image, you'll probably have to go back to the image domain before you can do the edges. Finding edges while remaining in the transform domain is pretty tricky. Whereas here, conceptually at least, one of the advantages is that you still are in that same domain, same time domain as before. So, so I guess the sampling side then, to kind of summarize this bit, every sample collected is energy spent in collecting it and energy spent in processing it and sending it and whatnot, okay? So instead of collecting it, could we prevent collecting it to begin with is kind of a helpful perspective to have. And as these works have shown, kind of compressive sampling and adaptive sampling or whatever, Lebesgue sampling, it buys quite a bit in savings, particularly because lots and lots of signals in our lives are inherently lower dimensional. Okay, they appear to be artificially high dimensional, but deep down they are just, I mean, if you think about like ECG signal, right? I mean, your heart can be modeled as a relatively simple electrical circuit with some sort of you can have an equivalent spice model for it, right? I mean, it does keep varying and all, but at any given moment it is reasonably lower dimensional. So, and the same is true for so many other things. Okay, so one should take advantage of it because it carries lots of gains. Subsequent work in compressive sampling has also looked at ideas like how can I do computation over compressive samples? Can I do machine learning over compressive samples? Can I do computational statistics over it so that you don't even have to reconstruct it back? You can just compute. If I'm interested in f of x, but I'm giving you compressed x, can I just compute f over the compressed x and get back the result? So those kind of things can be done. And in the control side, this adaptive sampling work has done. Another idea that I have seen is, remember that random matrix that I said for compressive sampling? What if that random matrix was secret, if it was key? So so there is connection between compressive sampling and crypto that also emerged. It basically becomes a vehicle for you to obfuscate things as well. So there are a whole bunch of ideas and all that have emerged in the last whatever decade or so in this space. Okay, let's take a short 5-minute break, and then we are going to move to how to process the sensor data. So 5 minutes.
Yeah, 7 days. Even 7 days is like pushing it. And
So there is just one rule.
Hi.
So I'll send you my resume on Candes.
Yeah, I will. I'll get back to you.
Okay, thank you.
And also, your other board.
The other board.
I think it's being delivered this afternoon. So at my home. So
Okay.
I should have it for you tomorrow.
Yeah, we can get it on.
Tomorrow. Yeah.
After.
Yeah.
Professor, did you get any matrix boards?
Hmm?
Matrix boards?
No. Oh, they haven't arrived yet. Did you check with
Yeah,
Tricia?
they were ordered on the 15th.
Hmm?
They were ordered on the 15th of February.
Did it arrive? No. But yeah, I forgot to look at my home, so you should send me an email so that I look. I don't remember things by the time I reach.
So you might have some at home.
Hmm?
You might have some at home.
I'm pretty sure.
Okay, I'll send you a
Mhm.
list of them.
No. Because whenever I order things, I order like one for myself, and then I promptly take it home, and then it disappears.
Right. I'll remind you.
Hmm?
But I'll remind you.
Yeah.
Embedded systems house.
Hmm?
Embedded systems house.
Yep. Embedded Systems House. I was doing a network scan of my home a few days ago. I have more than 200 IP addresses active, and I don't even know where they are. So.
Do you not get like flagged by FBI or Sine?
Hmm?
Do you like not get flagged by
Flagged by the
FBI or
NSA?
Sine?
Well, all I can say is if you want your PhD, don't flag me. Okay, so yeah, I think these are all sort of stuff all over.
Like, don't they like know that so many activists?
No, they're all behind a firewall. I mean, they're not on the. I have a single IP address and I firewall everything.
255 device like opposite.
Huh?
You can have 255 devices. Like,
No, you can have any number. Once I'm behind a firewall, I can have. I mean, you can have 2 to the power 128 IPv6 addresses. Sure.
Oh, 128 data.
Yeah.
So is it a hassle to upgrade everything?
Of course it is. Why do you think I don't know what most of those devices are? Right? I mean,
Get an IP number from one of them.
yeah.
So what kind of things are you doing that you could have 200 devices?
Well, firstly, I have lots of cameras.
Oh, okay.
Okay. And I have 4 or 5 Amazon Echo of similar number, and then by the time you count my whole family's phones and laptops and all, there's probably another 20-ish or so. So yeah, and then bunch of sensors of different types, door locks, stuff like that. Yeah, cars. Yeah, so everything has an IP address, really.
Do you log all that sensor data somewhere?
Nope. Why would I?
You can actually like give a data set like
Yeah. Okay, let's back to work. Okay, so next topic. Moving on. So we have now collected the data efficiently. So next up the stack is making some inferences out of it, right? Because so there's an interesting thing out now, which is ultimately why do we capture sensor data? Because we seek to make some decisions of it. And you can think of that decision making as kind of like a control problem, right? Okay, so it could be either control a motor or a drone or whatever in an immediate sense, or maybe the decision could take the form of collecting information which results in a new law, and that law affects the society, and that changes the society for the better. It's also a control system at a longer time scale. Or it could even be that It was used by scientists to formulate a better theory, and that changes our view of how the world works and results in a better system. That too is a control system. So eventually, any data that we collect is for some purpose, some decision making, and at some time scale, it kind of ends up affecting things. But still, it's kind of useful in many cases to break this cycle up into a sensing phase and an action phase, right? Although some of the work which is occurring now in some contexts does begin to look at things end to end. That is, sensor data collected, I push it into a computer, outcome is an action which is controlling an actuator, and I kind of bypass this whole middle thing. So some recent work in areas like autonomous driving and drone flight control and all is beginning to have that. So they basically put a neural network, feed the raw data to it, and the output is an action resulting from it. So just to take an example, let's say you are looking at the problem of keeping an autonomous car in the lane, kind of this smart steering control, if you may. So one way to do this thing would be to break up the problem. You basically say that, look, I'll put cameras on my car. They will tell me, they'll detect the lane marking. They will measure where the car is relative to the lane marking. And then based upon that information, I'm going to, and perhaps measuring the speed of the car, so some speed sensor, I'm going to then control the steering wheel such that the car remains in the middle, right? It's a very reasonable approach to doing it. In which case I have decomposed things into a sensing phase. I'm measuring the lane marking, I'm measuring the distance from the lane marking, I'm measuring the speed, and then I'm applying some human logic together with some simple control strategy to kind of control the steering wheel. The other extreme is, what if I were to simply feed the video from the camera and the sensor data stream from the speed sensor, and the output is the control for the steering. I mean, just bypass everything in the middle, no human engineering, just directly. And that kind of approach has also emerged now. NVIDIA, for example, a year and a half ago showed these kind of systems also. So there are things changing where instead of decomposing into these separate steps, you just go straight raw sensor data to direct actuator command and just kind of bypass the whole thing. But we are going to stick with the more conventional viewpoint, that is, we want this intermediate sensor data, and particularly because in some cases, in some systems like those policy making and scientific theory discovery, the control loop is such a long time scale that if I were to wait for those loop to finish, then I may not even realize that I had bad sensor data and stuff like that, right? So it's kind of useful to have a sensing viewed as a separate phase. So when we look at sensors in kind of our systems, they very broadly kind of fall into two categories. There are sensors which tell a platform, so think of it like the platform being a robot, okay, kind of a representative of a general embedded system. So there are sensors which tell the platform about its own state, its own speed, tilt, direction, stuff like that, okay? And then there are sensors which tell the platform about the external world. Well, how many people are in this room that I am, stuff like that, what color the walls are, so those kind of things, the context there. So the former category are called as proprioceptive sensors, basically one's own, okay? So example is temperature, speed, stuff like that. And extraceptive sensors, which are basically telling you about the outside, and both are important for us to do tasks, right, in a safe manner. Our body has examples of both, right? I mean, we have extraceptive sensors, we can hear, we can see, those kind of things, and proprioceptive sensors. Anyone? Examples?
I have the ear.
Huh?
Like the balance. Like
The balance, right? I mean, that's a great example, and of course, pain, stuff like that, right? I mean, these are all examples of proprioceptive sensors. All these sensors suffer from kind of a common set of challenges that they are not ideal. They at the very first level, they suffer from noise and calibration and lack of conditioning and all those kind of issues. So, of course, sensors are in our system are sensors in embedded system traditionally had been kind of fairly simplistic. Nowadays, we have really kind of fancy sensors, if you may, and of course, camera is kind of representative of the most sophisticated type of sensors that you might imagine. But oftentimes your sensors are just really trivial stuff like photodiodes and temperature sensor and stuff like that, kind of simple scalar quantities. And you use them to measure different things, and then behind them is sitting our friend A to D converter, which we are sampling using the strategies that we decided. And somehow you convert the physical signal into a voltage waveform that is kind of measured. So for example, I may have a resistor which is sensitive to light, and so its value is a function of the flux falling on it, and as this resistance changes, the voltage changes, and therefore the A to D converter reading changes. What is bad about this?
You might not know what the value of the resistance is.
Let's say I know.
Constant going
Constant drain current, yeah, this is lousy from power perspective. There's always current flowing here. Okay, so you also need to be efficient, and this is not a great example from that perspective. Okay, the other thing to keep in mind is that what we are really interested is not the sensor reading. We are interested in state of something, right? Am I imbalanced? What's the direction, right? I mean, there's some attribute, some state about the world that we really wish to know, as opposed to the raw waveforms, because the raw waveform is just some chemical, electrical, mechanical signal, right? And you have to translate that into kind of that state information. So I may be interested in something like, is someone, okay, this slide is messed up. Just a sec. Okay, so I may be interested in, like, is someone sitting on a chair? Okay, am I sitting? Am I walking? Those kind of things. But that's not what the sensor in my watch are telling, right? They're giving me signals like acceleration reading and gyro readings and all. And so you want to bridge that gap to get to the state of interest. You are trying to really infer the state, infer the context, and right. So that's really the sensing problem. So sensors will tell you these kind of things, right? Whereas what we are interested in are these higher level concepts, and how to achieve that is in effect kind of the major part of the sensing information. The other thing to bear in mind is that since our goal is to measure, to learn the state, there might be many different ways of potentially doing it. And so again, like, take some human type things. Am I stressed? Am I tired? These, right? I mean, is a particular person tired? These kind of things could be measured in many different ways with vastly different sensing modalities. Let's take something very simple. Where am I in this room? A particular individual. Okay. There are a variety of different ways you can imagine going around solving this problem with many different engineering trade-offs. Am I wearing something? Is that something that I'm wearing, is it allowed to transmit or receive only, or is it a purely passive thing? Can I instrument the room? Who needs to know the location? I or some infrastructure? All these kind of questions end up dictating even when it comes to physical properties, which go one level lower, right? I mean, from which you derive the inference. Again, there might be multiple ways to derive things. Like, let's take sound level. Want to measure how much sound is out here. So microphone comes to mind. I mean, that's what we normally use. It's kind of a magnetic diaphragm which kind of vibrates and causes a change in electric field, which is picked up by a coil, right? That's what microphones are. Can you think of sound level some other way?
Like a sensor?
Yeah.
The pressure, vibration.
Yeah. So it's ultimately sound waves. Sound waves move things. So anything which can pick up vibration, so accelerometers pick up vibration. So accelerometers actually can pick up sound levels. A lot of work has shown that with a noisier signal, but you certainly can, right?
Actually, I was trying this in the lab the other day, and we couldn't find like accelerometers that like normal like human beings.
Say it again.
So we had the accelerometers in the mobile phone, the apps that you have. So we kept that on a table, and then we started talking with each other, and we tried to see that it can it pick up those signals.
Yeah, so some of it depends upon the coupling you have and what kind of table and all that you have.
So do you need like very sensitive?
Yes, partly yes. Also, like even trivial things like, I mean, the cover on the phone may cushion things out. The size of the table, because most of these things are picking up vibrations from the surface that the object is, that your phone might be sitting on. But I mean, again, in our lab only a lot of prior work. I mean, we have had live demos of this stuff, so yeah, it works. Okay, I mean, yeah, it's a pretty old observation. I mean, a lot of papers and all have done it. So both gyroscopes and accelerometers kind of do pick up sound. And same thing pretty much holds true for any of these things. Light level, I mean, I've listed photocells and cameras, but there are other things potentially. You can even imagine light level affects some chemical reaction, and then you are picking up the signature of that chemical reaction. There are a variety of different pathways that you could go to these things. So I was talking about measuring my location, kind of a closely related measuring distance to an object. And there are a whole bunch of examples I have cited, right? I can bounce a sound wave off that. I can bounce a laser, infrared, those kind of things. I can look time of flight. I can look at the return signal strength. I can do cameras, right? Do cameras, kind of, okay. I can even do with a single camera. If I give you a single image and we bring some prior model, right? Human beings tend to be, I don't know, average human height, let's say 5.5, 6 feet. So if I show you a photo, I can basically make a guesstimate with related other things, how far away the person might be. So that brings another aspect, side knowledge, right? You don't measure things just solo, right? There is no such thing as a distance measurement. All of these things are relying on something else, like ultrasound one is relying on our knowledge of travel time of sound. So you can bring to bear additional knowledge. And there are many others you might imagine, right, of ways of measuring even something as simple as distance. Other things, as nowadays it has become quite fashionable to even attempt to measure things which are non-physical, like behavior, emotion, those kind of things. So they tend to be far more complicated to do it. Another one, take detecting people. Okay, again, cameras. So let's imagine I want to keep track of how many individuals are in this room. I could design the system in a variety of ways. I can have a camera up there and kind of looks at the image, maybe does some face recognition, not face detection, or maybe some other ways. Maybe it has a model of an empty chair, and then wherever the chairs are different. There are a variety of ways you can imagine just designing a system like that. Alternatively, I could also say, hey, I will just count how many people are entering and leaving this room by having some sort of a beam which is interrupted whenever someone enters or leaves. So I can approach the sensing problem in a variety of different ways, and they'll all have different consequences on privacy, efficiency, processing requirements, robustness, kind of you name it, right? If I just have the laser beam system, that will probably run into trouble detecting whether someone is entering or leaving. So I'll need to have something more complicated. Camera, on the other hand, is perhaps more robust, but if I were to have a camera out here, we'll all feel a little bit queasy, and it will require a lot more processing. So these kind of trade-offs, and in some environments which are cost constrained, that is an issue. One place where we see this thing playing out a little bit is as autonomous vehicles are coming into play, there's a lot of interest in this issue of the human interaction with the autonomous vehicle, like taking over when there is an impending problem which the car cannot handle. So different cars are approaching the issue of is the driver engaged in a variety of different manners. So for example, some cars are putting a camera up there. So they're continually monitoring and including perhaps your eyes and stuff like that and seeing, are you distracted, are you not paying attention, are your hands on the steering wheel or not. So heavy duty sensing brought to bear on that problem. The other extreme is like Tesla, for example. It tries to detect whether your hands are on the steering wheel. And even that it attempts to do rather cheaply by not having any sensor for detecting that you are grabbing the wheel. Instead, what it does is it tries to detect whether you are applying subtle forces on the steering wheel when our hands are there. So it's not like you have to basically kind of do subtle movements, essentially giving car the feedback that you are in control. And if not, it kind of barfs after a bit, warning sign, take over, otherwise it will stop.
So are you able to just use your legs? And
Some people have attempted doing it. I've also seen on websites gizmos being made which do it on your behalf. I mean, anything a human can do, a robot can do, right? I mean, so people have attempted doing that also. Question, yeah, so sure, you could. But they took this approach and with all its attendant failures, like the one you are pointing out. On the other hand, if it was an actual sensor, then might detect physiological signals, right? I mean, the steering wheel can detect, is the blood flowing through this hand, right? I mean, stuff like that. Or if it was a camera, it can detect whether there is a human being there or not, right? I mean, stuff like that. So approaching these problems can be an interesting exercise, and sometimes whatever. I mean, Tesla is trying to save maybe a $5 camera on a $100,000 car, right? I mean, it seems kind of odd, but these are whatever. How much money you, huh? It adds up, exactly. Yeah. On the other hand, I think the camera one is in the Audis. I mean, so in any case, variety of ways to approach the same thing. Or another one is camera versus radar versus LiDAR for the external monitoring around a car. That debate is also playing out, and they all have different strengths, different failure modes, different cost structures. The LiDARs tend to be super expensive. Kind of the some of the LiDARs are like $200,000, so more than your car. Okay, so but on the other hand, they do active probing of the environment and have some strong advantages over just a standard camera or radar. Okay, so sensing can happen in many different ways. A very common application, particularly in the so-called ubiquitous computing arena, has been of detecting activities in a space. So essentially, imagine like a home or a assisted living facility or a hospital or even an office environment, and what we are trying to detect are activities in such a space. People sitting in chairs, is a meeting taking place, are people talking, all those kind of stuff that you might want to know, so that the environment can react in an intelligent manner to that. So usually there are again, kind of in line with what I said a few minutes ago, there are many different ways the relevant sensing can be done, and people have attempted all these kind of approaches basically. So one perspective is dumb environment and people are instrumented. So we have smartphones. So one extreme is, can I just detect all these things with the smartphone? Okay, well, maybe not. Maybe, okay, let's allow for something wearable. So okay, maybe smartphone plus a smartwatch of some phone, or maybe some other things like at present, when I look at kind of the wearable sensors which I can buy today or like have, they include rings. There are several companies selling sensor instrumented rings. Earbuds with sensors, several companies selling those. Necklace pendants, several companies selling those. Badges, so like they kind of like pendants, I guess, except not as fashionable looking. So okay, so that's another one. Shoe inserts, that's another one. I don't know, I'm sure belt level stuff, those are also I've seen. So there are probably, I don't know, half a dozen, maybe 10 different forms. Oh, eyeglasses, that's another one which exists. Google glasses kind of failed, but there are some other ones out on the market still. So there are some fair number of examples where wearable plus thing, and you could imagine that cameras, wearable cameras of some form, right? I mean, maybe on the eyeglass or something can kind of go a long ways also as well. The challenge though is that in that case the human has to be present, so which is not always sufficient. So maybe some level of instrumentation in the environment is also necessary. So the other extreme comes from people who try to instrument everything. Okay, so I have seen places where like every piece of furniture and every drawer and every door and window and every appliance and everything is just instrumented. Okay, and probably kind of there's a middle ground, but there are lots of things that can come into play. So let me throw out a simple question. Okay, there is an oven or a cooking range in a kitchen, and you want to detect cooking activity. The range is in use. Okay, tell me some ways you can go around doing it.
One is that we can listen to a microwave, the door opening and closing.
Okay.
Microwave itself running.
Okay, I think you do all the cooking on microwave. Okay, but that's
No.
okay.
And like burner turning on and off.
Okay, so that's what, sound or what?
That's sound, yes.
Okay.
And then temperature sensing.
Okay.
If you learn the pattern of someone maybe cooking, you have a video camera and stuff.
Okay, so camera.
Like laser beams, so that you cover several different areas of the kitchen, and you can actually like detect which area is like used most. So like that type of activity is like done more. So closer to the sink, or like closer to the microwave, or like closer
Okay.
to the
Okay, so your motion patterns there. Okay. My wearable, maybe there's some cooking action you can detect. Sound. Another very powerful one is electrical signatures. I'm assuming, let's say the microwave is certainly electric, so you can monitor the pattern of the current in your central meter and detect appliances. It's an area called non-intrusive load monitoring. So you can actually from outside the house, like electric utility company can detect what all is happening in your home.
Most practically, wouldn't a company just put an IMU in some small wearable and then have a pattern where, you know,
Yeah,
what is
but you have to get the people to wear the IMU, right? Okay, so the thing is the answer to a lot of these things also depend upon who is sensing, what cost you are willing to pay and stuff like that, right? I mean, all those kind of things come into play. Another one which sort of I've seen some researchers kind of struggling with a little bit right now is so these are people in dentistry, oral health, and they want to keep track of proper brushing hygiene. Okay, so are you brushing properly and doing all the quadrants for adequate amount of time and stuff like that. And again, it turns out to be kind of non-trivial problem to kind of get right. Or things like a very hard one actually has been detecting eating. Okay, so for people who are trying to lose weight or are on things like congestive heart failure and these kind of diseases where the eating habits matter, is there a way for us to keep track, kind of an auto log of what you ate and drank? Okay, ideally. Okay, so because humans entering into a diary of some form is pretty error prone and people lie. So is there a way to kind of go around doing that? There are a bunch of examples of incredibly hard sensing problems and also doing it in a manner which is comfortable, not too problematic from a privacy perspective. There are a whole bunch of issues that kind of come up. So in this setting, you see that, but again, you'll find that there are examples, and there are several universities have model environments where they have or installations where they have deployed these sensors very heavily. Georgia Tech on its campus has something called an aware home, which is basically a home where people live, can live, I guess, during the course of the studies, okay, but heavily instrumented, everything. They have sort of sensors in every drawer and every door to detect their opening, closing, stuff like that, okay. Another group which has stuff like this quite a bit is Washington State Pullman. They have, I think it's called project called CASA, where they have a whole bunch of apartments in their city, instrumented pretty densely, okay, and kind of a lot of useful traces and all. And there are a lot of groups in Europe and other places which have done these kind of things. So sensors in the environment is one approach, and sensors on the body is the other extreme, right? So when it comes to the body, the most common sensors which get used are the ones which are detecting physical motion in some form. So accelerometer, gyroscope, and magnetometer, and then at a coarser scale, GPS give you motion related data, and you can broadly separate these things out into kind of fine motion and coarse motion, okay. Fine motion tells you a lot, like for example, and so does coarse motion, right? So for example, if suddenly someone stops going out much from the home, or so that can pick up problems like depression or certain types of sicknesses and all. When it comes to fine motion, it turns out certain diseases like Parkinson's disease and all, which are kind of motion related, their signature begin to manifest themselves. So health related aspects, safety related aspects, all of those things come into play. And then you can measure physiological signals directly. So you have heart rate, which is obviously tells us about the heart rate. You also, I guess, even a more primitive level, you have the ECG signal from which you can derive the heart rate. You can also derive the heart rate from a signal called PPG, photoplethysmograph, which is basically what your Fitbits and all do. When they shine a LED light, look at the reflection, analyze that. You can get it other ways also, because you can imagine mechanically, like your heart thumps, so there is perhaps some motion that could be detected. There are radars which can detect the beating of the heart, because they can detect those subtle motions. So in fact, there are sensors which can detect a beating heart through concrete and miles away, through foliage and all. So they are often used in rescue missions and war fighting and all. Heart rate variability. This is a variation in heart rate, d over dt over the heart rate. Why is that useful? Anyone?
Fibrillation, I guess.
Huh?
Arrhythmias?
No, not quite. Kind of, yeah, but not quite.
I think it can tie to stress to an extent, right?
Okay, stress, yes, absolutely.
Exercise.
Fitness, okay, fitness level. So in fact, when it comes to how fit you are, your resting heart rate is important. Go measure it sometime. Lower the better, up to some extent, right? So athletes have pretty low resting heart rate. And the other thing is heart rate variability. You want high heart rate variability, okay? But the thing is, there is no absolute number, it's relative, okay? So HRV is used by fitness enthusiasts, cyclists, those kind of people, but it's a good measure for everyone. And then stress, indeed, as you said, that psychosocial stress also has signatures on heart rate variation. Breathing rate, what all do you think breathing rate can tell us?
If a person is like doing heavy work.
Okay, dead or alive is first thing, obviously, but what else?
If a person is doing heavy work.
Okay.
Stress is also.
Stress, yeah.
as one of the-
Conversation, okay. Eating,
Sleep apnea.
sleep apnea, okay. There are a whole bunch of things you can imagine with breathing rate which can come up. Some of these things also play into things like detecting seizure after taking drugs and stuff like that. So like opioid related issues, and also some of these sensors are coming into play there. Galvanic skin response, that's the conductance of the skin. What all does that tell us?
The person is sweating.
Yeah, and you sweat when you are stressed, so it's actually about stress. lying, right? This is a lie detector test, right? Well, so that's really stress. I mean, the lie is not really detecting lying. It is really kind of stress, really. Okay.
What does a polygraph test actually measure?
Sorry?
What does a polygraph test actually measure?
Well, a bunch of these signatures. So heart rate also, and also the galvanic skin response. Okay. Blood pressure, again, as you can imagine, a whole bunch of things. EMG, this is the electrical activity in the muscles. EEG from the brain is picked up on the scalp, and then you can imagine more intrusive stuff. Almost everything imaginable here, people have tried out. Now, some of these things are pretty intrusive to measure or inconvenient to measure. Like take, for example, ECG, right? Kind of the gold standard really is having leads attached to your skin and kind of uncomfortable to say the least. On the other hand, some of these things can be picked up by wearables. Some of these things can even be picked up remotely. So nowadays there is plenty of work which basically shows that Wi-Fi access points and all can be retargeted as radars, RF sensors, and they can measure some of these things, right? Heart rate and stuff like that. So a lot of so a lot of those things are happening. Interestingly, a lot of these things can also be detected here as well, right? I mean, there are some of the things we try to detect have other signatures. Most things manifest in multiple modalities, and therefore one could conceivably pick them up in multiple ways, or you could combine the signatures from multiple ways. And then, so for example, I mentioned that breathing rate could tell me things like which affect the breathing, so like conversation, smoking, those kind of things can be manifested out here. Let's take smoking. So you take a puff, right? So that would impact out here, but probably accelerometer can also detect it with the motion of the wrist. Okay, combined perhaps with your GPS location if you are in a known smoking room or something like that, right? I mean, so same thing could be detected kind of multiple different ways. And part of the challenge again in designing these things is to strike kind of the right balance. One risk and temptation, risk from temptation often is that throw data at it and then assume that good things will come out of it. Often that's not the case. The art of designing a sensing system also is to identifying which modalities are the best ones, okay, as opposed to simply taking all the data you have and then hope that machine learning algorithms can figure things out. It doesn't work that way. So that level of domain expertise and all is often important. So lots of immensely cool work happening in sensing nowadays, just because we are trying to provide these kind of responsive applications, if you may, all the time, anywhere you are, right? I mean, we have this desire, there is this whole movement that also exists called self-quantifiers. Okay, these are people who try to measure everything about themselves all the time, essentially creating like a data cloud for themselves. Okay, because there are, and there's tremendous interest in that from medical community and as well. So besides kind of just smart homes and all, it's really also related to that aspect also. So I'm going to talk about now how do we go around inferring these things on Thursday. So see you guys then.